All right, so we're going to talk about moving fluids, and the fancy name for this is hydrodynamics. So that is the branch of science that concerns itself with how to study moving fluids. So there's two types of moving fluids. So the laminar flow, which means smooth, and then turbulent, which is not smooth. Now, these are not scientific definitions. Not laminar. So the best way you can think about it is the pattern of laminar flow doesn't change. So it's sort of like if you turn your spigot on in your kitchen, you can think of that as laminar flow. It has the same pattern. What's turbulent flow? Turbulent flow might be something like if you go down to the river where there's lots of rocks, or maybe you've seen white waters before, and you have this water that's rushing and it's bouncing all over the place. Those are two drastic sort of examples. You could think of turbulent flow as something that changes abruptly, whereas laminar flow doesn't. It's steady, it's smooth. So we don't care about turbulent flow here. It's way too difficult to study. So we don't do that. We're interested only in laminar flow. So okay, so if we're going to talk about a moving fluid, what you need to have some sort of idealized thing of what this means in your head. And so the best example I can tell us to think about is just imagine we have water moving through a cylindrical pipe, or you have water moving through a hose. And that's a good thing to keep in mind, because that's a simple model for even something like blood moving through your body in your arteries or your veins. And so if we're going to talk about something moving, we want to have a visual. So just like we did last class, we have to pick a simple visual that can extend to more general settings. So here's our visual. Imagine we have some cylindrical pipe or hose. So let's say it's moving left to right in a hose or pipe. So let's put some blue in here, make it look pretty. So here's my piece of water I'm going to examine. It's moving. So the obvious thing that comes to our mind if something is moving, we might say, how fast is it moving, or how much of it is moving? And so these two questions sort of stimulate the idea that we should have multiple ways of envisioning, or multiple ways of quantifying what's happening, or describing analytically what's happening. So the first sort of obvious, I don't want to say obvious, I shouldn't use that word. That's probably because it might not be obvious to you or obvious to anybody else, but imagine if you said, okay, I'm going to go to my bathtub and turn it on. What kind of ways can I describe what's happening? One thing you might ask is, okay, how long will it take to fill my tub? Or, I mean, how deep will the tub be after 2 minutes? I mean, these are some, just some generic questions, but how could you possibly answer them? Or what information could you deduce if you timed how long it took to fill up your tub? Or you took a measurement after so many minutes of the depth. So, one way to characterize what's happening here is to make the following definition. So flow rate is the volume of fluid passing a particular point. Now I'm going to put the word point in quotations because I'm using it in this colloquial way. I don't necessarily mean a dot on the paper. I just mean a spot in the universe. So maybe you can think about the point in quotations as like, say, this red line right here. So when we say flow rate, what we mean is we mean the volume of that fluid that's passing a particular point per unit time. So for example, you might say, I'm going to go study my bathtub. Maybe I'll measure things in gallons per minute. How many gallons can I fill up with my spigot? Can I get 1 gallon a minute? 7 gallons a minute? So imagine I have that red line and I say, okay, that little blue thing I've circled in, that's 1 gallon. And suppose it takes that 1 gallon, or maybe 1 cubic meter if you want to use SI units. Suppose it takes 3 seconds for it to move past that red line. Well, then we would say the flow rate is, 1 gallon per what? Well, if it takes 3 seconds, then you would say 1/3 of a gallon per second. Once again, this kind of goes back to what I've stated since the very first class. One of the most important sort of like tricks I can teach you, and I don't want to say trick because that's really a bad word of saying it, but is to always think about units. So what I would encourage you to do is think of flow rate in a formula way. So flow rate equals volume over time. That's the way I would encourage you to think about it. Now, this is different than, say, speed, right? Because speed, how do you measure the speed of a fluid? Well, you might say, okay, let me take 1 molecule of that water and see how fast, or excuse me, how far it travels over a second, or excuse me, a unit of time. All right, so so it's worth us reminding you of that. So note flow rate is not speed. They are related, though. We're going to see why and how right now. Does anybody have any questions or concerns, comments?
I'm out.
I like it how once in a while when I ask that, someone will chime in. This is so good. Everybody else is sleeping. Who knows? I should be sleeping right now. It's Monday morning. Such a fabulous weekend of insanity. All right. I wonder if Poker Stars knows I'm wearing this shirt. Should I get I should get paid for this. There's how many of you in this class? 20. This is free advertising for them. It's a 20-year-old sweatshirt. Okay. Sweet. Okay, so remember, what is speed? Speed is distance traveled over time. That's sort of our generic definition of speed. So as I said, we might say, okay, if I go back to my picture, we might think of speed as, if I go from this red line to, say, I color in a green one, we might say, okay, how long did it take us to get from the red to the green? That would be how we define speed. And so what we know is, and it sounds funny, I keep using a bathtub is sort of the thing for you to visualize, but it's really true. It's also worth it this time of year. I don't know if any of you have flowers. I have flowers everywhere in my house. That's what happens. And I got to water those damn things all the time. And if you have I don't want to say fancy, if you have a standard hose nozzle, what happens is you squeeze it in the water, you could change, at least visually to your eyes, how the water comes out. Just like if you have an adjustable shower head, you might spin it so that it comes out and it is stronger, or comes out like a shower or a mist. And so the physics that makes a hose work or makes a shower head work is that you have a specific flow rate moving through the pipes. And then what you do is you limit where it can move. And so what that naturally does is it increases the speed of the fluid. You probably all at one point in your life had a hose in your hand without a squirter on the end. And you guys know if you put your thumb at the end, what happens? You can turn and increase the pressure if you want to. Sometimes how we explain it. So what we would like to do now is sort of quantify those ideas. How do we describe what we see happen when we take a hose and pull the trigger, or when we take a shower and we adjust the dial of a shower? Then again, maybe some of you never did that. Maybe some of you shower with a non-adjustable one. I don't know. Anyhow, what we'd like to do is we would like to bring speed into the picture. So to do that, we take it this following way. So we're going to draw the following generic scenario. So to introduce speed, we use the following model. We have our cylinder here with fluid moving. And then what's going to happen is it's going to abruptly have to go into a cylinder of a smaller diameter. So maybe I should draw this more carefully to bring 3D into the picture. So this is kind of what I want you to think about. You have some fluid moving. This looks like a muffler to a car. So we have a specific volume of fluid. It's moving left to right. And there's going to be some distance. We'll call this guy. We'll call this guy L1, because there's going to be two of them here. And then what happens is when that fluid moves and it hits sort of that wall, it has to change its size. Remember, that's one of our defining things of a fluid, is it takes the shape of whatever it's in. And so what we'll do is once it goes into the smaller cylinder, as it were, whatever this quantity is, the thickness of it, if whatever you want to call it, we'll call this L2. And then for some for some clarity, let's note again, these are cylinders. So what's the cross-sectional area? This has a cross-sectional area of something. We'll call this A2. And then the bigger cylinder has a cross-sectional area. We'll call that A1. So I hope you all understand the problem or the scenario or the model, however you want to call it. And if you don't, please ask. This is sort of like a very simple model of what happens, again, when you squeeze a hose. You restrict the hole at which the fluid can go through. It becomes smaller. And so I'm drawing this picture looking ahead to what we know sort of happens. Now, I purposely drew L2 to look bigger than L1 because it's going to be. So what physical principle is sort of going to direct us here? So here's what we know. So we know, and of course this is provided there's no leaks. That the flow rate on the right and the flow rate on the left have to be equal. So if we go back to the picture for a second, what we're saying is the amount of volume of the water that passes a particular point in the big cylinder must be the same volume that passes a particular point in the smaller cylinder. So we know this must be the same. If you want, you can generically think of this as some sort of like conservation of energy type thing, where what's coming in, the flow rate has to be the same that's going out. So what we want to do now is we want to use this information, and we want to derive a useful formula from it. So what we're going to do is you can study each of these equations separately. So let's express each side of this equation. In different terms. So let's look at the flow rate on the left. What is it equal to? Well, we know it's equal to the volume over time. Now, let's be very important. This is the volume on the left. Now, what's the volume on the left? The volume on the left, if you go back to the previous picture, is it's the volume of this cylindrical piece of water. So its height is L1, and its cross-sectional area is A1. So if we write this a little more succinctly, this is going to be A sub 1 times L sub 1 all over T. Now, the key observation to make is that speed is hiding in this expression because L1 over T is speed. So again, if we go back to our arithmetic, I can write this as A1 times L1 over T, which is just equal to A1 times V1. So let's define what V1 is. So this is the speed in the big cylinder. Right, because think about that. That's telling us how far we travel, L1, over a period of time. So by definition, that is speed, distance traveled divided by time. So what you end up having is the same thing for the right-hand side. So flow rate on the right is equal to, this time, A2 V sub 2, where V sub 2 is the speed in the smaller cylinder. And so when you combine these facts, so if we know that the left flow rate and the right flow rate have to be the same, what you end up getting is you get the following. You get area, velocity in the one, or area and speed, I guess is what we were calling it, has to equal the second cross-sectional area times the speed in that particular cylinder. So this has a name. It's often called the equation of continuity. So this says a couple things. First off, it gives us the relationship to what happens when I mean, if you want to think of these as pipes, when the diameter changes, it gives us that relationship. But it actually gives us a relationship for any changing. I mean, the math would be much more difficult, but you can derive a similar sort of result, whether you're talking about a cylinder or any container that fluid is moving. So there's two things to take from this. You have this nice relationship called the equation of continuity. But if you go back a page, you also have, you see another nice thing is that flow rate is, in fact, directly, which you can even argue, proportional to speed. So flow rate being equal to cross-sectional area times speed is also very important. So keep that in mind. And how do we keep things in mind? We remind ourselves of it. So in the above derivation, we also get that flow rate equals area times speed in general. Let's put this, we'll make it, let's clean this up. Or if you'd like, you wanna understand what speed is. You divide both sides by the cross-sectional area, and you get that speed is flow rate divided by cross-sectional area. So now these formulas give you easy ways of solving problems. So now you can do the fun thing you've always dreamt of doing. You now have the math the next time you're giving someone a shot, or the next time you're putting an IV in someone. You now know the exact way to calculate the speed of the fluid or the medicine going into a patient. Aren't you just so excited to do this? When you hit the plunger on your syringe now, you can think about the medicine in the tube, and then the plunger pushes it into the needle, and you can now quantify that speed change and flow rate. Your lives are now changed forever. You will never administer a shot the same again, I'm sure. You'll be like Rain Man. You have all these equations in your head thinking, how can I do all this kind of fun stuff? So a standard problem you might get is one, if you look at, I think problem, let me look it up. Problem 8 on the homework is an example of this. So let's do one, and it's real quick, just so you can see what we mean by this. So say the barrel of a syringe has a diameter of 1 centimeter. We'll use simple numbers. And let's say the needle I don't know, what's a standard? Let's say, what, maybe 0.2 centimeters? I don't know. That seems reasonable. So suppose you press the plunger. So that the medicine moves, I don't know, 3 centimeters per second through the barrel. Let's determine the speed through the needle. So there's a couple comments we should make about this before we solve anything. How I've written it and that kind of stuff. So notice I didn't state it specifically, but it's not hard to deduce. I gave you the speed through the barrel. Notice the units. I said 3 centimeters per second. I didn't tell you the flow rate. I could have given you the flow rate, but I gave you the speed. And so then we're asking you to determine the speed through the needle. So that means that we have 2 ways we might try to solve this. And so you try one, and if it doesn't work, then you try the other one. But being that I'm given a speed and I'm asked to determine another speed, then I want to use the equation that has speeds in them. So the operative equation to use is, and let's draw a picture. Here's a picture of our situation. I don't know why I chose red. So here's our syringe. Here's this little plunger. That's a good syringe. Looks like one of my kids' toys. And so we have our little medicine in there. Here's our medicine. And so here's what we know. And this is the equation of continuity. We know that A1 V1 has to equal A2 V2. So let's imagine we're going left to right. Now, what we gave you is we gave you the diameters of both pieces. So you need to compute these areas. Now, every one of us has our own way we like to sort of solve these things. Some people might want to rewrite this as V2 equals blah so that you can just plug and chug. Some of us might want to compute all these values separately and then plug them into the equation. I don't know how you want to do it. I can't speak for you, but you have to figure out what's the simplest way for you to do it. So what I like to do, and this is just my own sort of personal way of doing it, is I like to write down what everything is. A1, we know what it is. It's pi times the radius squared. But what's the radius squared? That's half the diameter. So that's pi times 1/2 squared. We know what V sub 1 is. We're told, what did I say it was? Is it 2 centimeters? I'm sorry, what's V sub 1? 3 centimeters a second. So this is 3 centimeters a second. We know what a sub 2 is. It's pi times its radius squared. But what's the diameter here? It's 0.02 over 2. So half of that squared. So don't forget, what are the areas here? Well, we're using centimeters, so this becomes centimeters squared. And of course, this is centimeters squared. And v sub 2 is the unknown. This is what we're trying to determine. So again, what this problem essentially is it's a plug and chug. V sub 2 equals, if you divide, you get a sub 1 v sub 1 over a sub 2. And now this is just a calculator problem. So you go to your calculator and you plug it in. Again, I don't know how you like to do it. I would encourage you write these things out. So you have pi, and then this is 1/4, and then that's centimeters squared, and then v sub 1 is 3 centimeters per second all over. Down here you have a pi, and then 0.02 over 2 squared, and then centimeters squared. And lots of, again, this might be overkill. Maybe you don't like to write your units. I do, because I like to cancel things and see them cancel. And then I'm left with what? 3/4 divided by what is it? 0.02 divided by 2 squared. So let's think if I did this correctly. And so if we do this correctly, what do we end up getting? We get, make sure I didn't mess up. So it looks as if we get 7,500 centimeters per second. Seems like a big number. Question is it realistic? When you're doing these problems, you should always ask yourself. I mean, if we're asking you to do a real world problem, is the solutions, does it make sense? Does it seem realistic? You know, if I calculated this and my speed was 3 times the speed of light, I would assume I did something wrong. But this is in fact realistic if you think about it. Does anybody have a question about this? I don't think we made any arithmetic errors. Again, you might have written your fractions differently than I did. You might, you know, that's just every one of us has our own sort of personal way of writing the arithmetic down. Okay, so Does anybody have a question about this?
No.
All right, so again, this is a very straightforward example. It's a plug and chug. It is what it is. Okay, so what do you want to do next? Okay, we study the speed, we study the flow rate. Then you ask yourself, okay, what other physical quantities are at play? And then you might say, okay, what we haven't talked about. If we know something's moving, we know that there's energy, kinetic energy specifically. And we also know if something's moving and has kinetic energy, work is also at play. And we also have things like force and pressure we haven't thought about yet. So we want to bring that into sort of play. So the next thing to consider is pressure. So again, we have the same model we want to imagine we're working with. You have some sort of pipe or hose. And you imagine it flows into a smaller pipe or a smaller diameter hose. So here's our fluid, and then we know when it comes over here, it grows a little bit. And so we gave names to these things earlier. You know, we can call this L1, we can call this L2. But now we want to think about what's happening, you know, at the ends of here. And so what we haven't talked about yet is you have some sort of force. We'll call it F sub 2, and we know what force is. It's pressure times cross-sectional area. And then similarly, you have it over here. So what we want to do is we want to look at work from two different angles. Or two perspectives. The first we're going to do is the definition. And then we're going to do it from the work energy theorem, which you might not remember. We'll remind you what it is. So again, we're going to write out and manipulate expressions for work in two ways. We're going to look at it strictly from the definition, and then we're going to look at it from the work energy theorem, which uses kinetic energy. Okay, so let's do that. So remember, what is the definition of work? Well, the definition of work is force times distance. This is the definition. And then we also know that work is the change in kinetic energy. This is the work energy theorem. So I'm going to write out work using both of these equations, and then we're going to use those equations, going to combine them to get a useful equation that incorporates pressure into our analysis, or allows us to include pressure as part of our what we're quantifying. So what is the total work of the system? Well, there's two things happening here. The work is going to be dependent on what part of the pipe we're in. In this part, we're going to have a certain amount of work done. We'll call work 1. In this portion of our cylinder, there's another work being done. And you can even imagine this from a very intuitive perspective. You know, if you were going to push something through a cylinder, maybe some liquid, you would imagine that it's going to require a different amount of pushing from you from one of these cylinders to the next. And then the other thing to understand, and I'm trying to illustrate that with these arrows here, is that F1 and F2 are opposing forces. Whatever force is coming from the right is opposite of whatever force is coming from the left. So one way we handle that, as you guys are well aware already, is that means we assign one a positive direction and we assign the other a negative direction. Just like when we're talking about objects going up and down, up is positive, coming down is negative. If I say there's an object that's, I shoot it up in the air and then it hits its height and falls back down, how do I know if I tell you that it's going 7 miles an hour? Is it going up 7 miles an hour at that point, or is it on its way down? And the way we distinguish is we use plus and minus. So the same thing works here. Since we usually attribute left with positive and moving right with negative, we'll say that this is work 1 plus work 2. And we'll say this is F1 D1 plus work 2. But work 2 is going to be opposites. The way you should think about this is force 1, distance 1 minus force 2, distance 2. Now, I didn't use any D's before. So if you go back to the picture, what really the letter we should be using here is this L1 and L2. So this is force 1 times the force from the left. And how far are we pushing it? Well, imagine that that volume of water is going that distance. And then it's going to be minus F sub 2 and then the corresponding L sub 2. Now, it's also going to be useful, again, remember, we want pressure involved, correct? So instead of writing this with F1 and F2, let's use the definition of pressure to say that, okay, this is great. This becomes P sub 1, A sub 1, L1 minus P sub 2, A sub 2, L2. Now, let me color code this so it's clear. This sort of stuff over here, this is the definition. I'm using the definition of work. Work is force times distance. Now, the issue is there's going to be two types of work being done through the first part and then in the second part. So I'm going to call one work 1, the other work 2. And then what I recognize is that the forces are opposing forces. So that means that I have to incorporate that. And the way we do that is using this minus sign. Now, if instead of using the definition, if I go right to the work energy theorem, I also get that work total is, as we know, it's the change in kinetic energy. But what is that? Well, that's 1/2 the mass times speed 2 squared minus speed 1 squared. Remember, kinetic energy is 1/2 mass times velocity squared. So again, what is the work energy theorem? It's change in kinetic energy. That means you take your final kinetic energy and subtract the initial. So that's why I have V sub 2 minus V sub 1 there. So now I have two descriptions of of the total work. Here I'm telling you the total work is this, and then I'm also telling you the total work is that. So in math, we call this the the commutative property, or the, I guess that's not the correct word. What am I saying? Must have had a stroke this morning. Anyhow, Hscg that from the record. But what we're telling you is that if I have the same amount of money as Andrew, and Andrew has the same amount of money as Tommy, then we can conclude that me and Tommy have the same amount of money, right? It's called the transitive property. And so since work total has two descriptions, that means those two separate descriptions must be the same thing. And so that's what we get. So if we combine these facts, so we conclude what? Well, we conclude that P1A1 stuff. So you can conclude that P1A1L1 minus P2A2L2 is equal to 1/2 M V sub 2 squared minus 1/2 M V sub 1 squared. Now here's what's even more sort of useful to understand. We did this with a cylinder so that the equations were simple, but as I said, you can do all this in more general settings. And what's another word for area times height? Area times height, that's the volume. And so what we can do is we can actually write this more generally as P1V1 minus P2V2 equals this. Now remember, and we're not done yet. We can actually do more, but before we do that, it's very nice to look at this equation and think about what's happening using only numeracy ideas from your brain. Basically, it's telling you what happens if the pressure changes to the speed, or vice versa. If you change the speed, how does that affect pressure? Now, here's what else we know. We know, and we talked about this in the beginning, we know that if you have a specific volume of water, it's not going to change. The volume won't change once you shrink it. It's not like some of the water disappears. It doesn't go away. So even though, if I go back to my picture, even though the depth of my cylinder here changes, the thickness once it goes from the bigger diameter to the smaller one, the volume has to be the same. So it must be that V1 and V2 have to still be the same number. Now their shape characteristics might have changed, but the actual size of that volume of water can't change. So it's important to note that. So V1 has to equal V2, so let's just call it V. So what you end up getting is P sub 1 times the volume minus P sub 2 times the volume equals this. So this is a very useful equation, but we can do better. It's worth sort of singling this out because it has some very nice properties. It tells you, think about it, volume is always positive. So think about what this equation is saying. If P2 is bigger than P1, if there's more pressure from the right, then the left-hand side must be negative. And then that tells you that the right-hand side must be negative. I forgot an M. So let me say that again, because it's probably not obvious what I mean. Look at the left-hand side. If the pressure from the right is larger, if P1 is bigger than P2, then the left-hand side will be a negative number. And if the left-hand side's negative, that means the right-hand side will have to be negative. And so that would force V1 to actually be bigger than V sub 2. So think about that, how that interplays. If V1 is bigger than V2, that changes exactly what you may, I don't want to say it messes with your intuition, but maybe it agrees with it, depending on how you're viewing it. So I would encourage you to think about that. Now, this is an ugly equation, and you might think, can we make it look prettier? And the answer is yes, you can actually make it look prettier. How do you make it look prettier? Well, what we're going to do is we're going to remember that mass, okay, that's fine. We know mass won't change, but there's a better way to get information from this. So what if we replace mass with density times volume? So we can get even more descriptive by using mass equals what? Well, mass is equal to density times volume. Now, is that fluid that's flowing, it's not going to change its chemical characteristics or its physical characteristics in the sense, well, the way it takes the shape of its container will change, but it's still going to have the same density. It's still going to have the same volume. So if you go back a page and you look at the right-hand side, if you replace M with rho times density, that what you end up having is P1V1 minus P1V minus P2V equals 1/2 rho V speed squared minus 1/2 rho volume V sub 1 squared. Now, every term, you have 4 terms in this equation. All 4 have the factor V in it. And one of the things you learned in algebra many, many years ago is if that's the case, you can cancel it out. You can divide through by it, or I don't know how you want to think about it, or you can factor it out and cancel. But that equation just becomes P1 minus P2 equals 1/2 rho V sub 2 squared minus 1/2 rho V sub 1 squared. So these are lowercase v's. These are my speeds. I'm getting sloppy, I apologize. Let me try to be more distinctive. So this is an extremely useful formula. It has a name. So this is called the Bernoulli equation, or Bernoulli's equation. So if you just ponder this thing for a while, hopefully you will. I don't know that you will. Maybe you'll try to do this derivation on your own. I hope. I don't know if you will. But it's very telling how things. I mean, could you describe in English what this sentence, the mathematical or the physical sentence, is saying? I mean, think about it. If pressure decreases, what does that say about speed? Or if speed increases, what does that say about pressure? Can you understand how these numbers play and affect the other one? Just as you would imagine, what's going to change, what's going to affect pressure? It's going to be speed and density. I mean, that makes sense to us. Would we not assume that the density of a fluid is going to affect the pressure that's created? Or, I mean, it's intuitive to us. And what's pretty cool about this is it naturally falls out as long as we use the definitions and follow the basic algebra. We get this Bernoulli equation, which is essentially it's loaded with this information, and if we study it and we make sense of it, we'll realize that the information it's telling us is exactly what we would expect to happen, even if we're thinking of ourselves as 12-year-olds putting our hand at the end of a hose. So maybe that's what you do today. You go out and find a hose, go to Home Depot, buy a hose, and sit around and put your thumb at the end of it and say, hey, Bernoulli's equation. Okay. And by the way, this is a sort of a, I'm not being completely honest, but this is sort of the equation that in many ways helps describe how, for example, airplanes fly. You know, think about how airplanes work with what's called lift. You have speed increasing, and that changes the pressure differential below and above the wing, and that creates what's called lift. Now, I'm not saying an airplane flight is as simple as this equation. That's all I'm saying. But the underlying principles to how it works can be traced back to these ideas. Similarly, in storms, you know, a lot of times you see these bad storms and maybe a roof gets off a house or windows break, and we might say that it's the wind that does that. Well, yeah, but it's more indirectly because the increased winds cause a pressure change inside and outside of the house. So there's definitely an interplay between speed of something, whether it's wind or water, and then the pressure that's created. Okay, any questions about this? Okay, I didn't even check to see if some, no. So one of the things that we're going to ask you to do is let me make sure it's on there. Make sure I didn't lie to you. Great, I asked you to do that for homework. Problem 9 is how does a Venturi tube or a flow, flow meter is how do we measure the speed of fluids in pipes, for example? And so I'm hoping that you will take the time to do that, describe it. There's a picture of it in your book. It's pretty simple, but the reason I want you to do that is it also relates to what we were talking about earlier with the some themes pop up in it. So hopefully, you know, you guys can get that locked down. If not, we can go over it on Wednesday. Does anybody else have a question about this Bernoulli equation? The reason I kind of don't want to do the Venturi tube right now is we just spent a lot of time doing algebra. Maybe you're algebra'd out. I don't know. Probably. But I hope you look at it, and I hope you take some time to see how this equation affects or is involved in that derivation. Hopefully you'll do it. Okay. So what's next? So here's a hidden little, not hidden secret, but what time's at 10:20? So in the previous work, all it is it's just a simple model. So I use the word simple. Very colloquially. To be more realistic, we have to understand that things such as friction would affect how fluids move. Right? In fact, from the obvious medical thing I can consider, or I think this is correct in saying, and maybe I'm wrong, you can correct me if I say nonsense. But if we're talking about blood pressure and how blood flows through your arteries, and if you have plaque buildup in places and it restricts flow, friction and things like that can really play a role on how water or any fluid moves. So to be more realistic, what we must do is we must not ignore friction. I mean, as you would imagine, let's draw a simple picture. As you would imagine, if I have a fluid flowing in my cylinder, that friction sort of builds up because it's going to be moving faster closer to the center. So one way of saying that is fluid is, and I'm using these words very colloquially. So the fluid is slower near the surface of the cylinder. So this introduces a new thing called viscosity. So what we do is we define viscosity so this is the number when we use the Greek word eta. And it satisfies the following. P1 minus P2 equals A pi eta VL over A, where L is the length of the pipe or the cylinder, and A is the cross-sectional area. So I'm going to spare the algebra, but we can solve this thing for V, which maybe you'll do. There's some good things you might ponder. Why is there an 8 pi in there? These are questions that you should ask and think about. I don't know why I can't spell properly. I need spell checker on this app. Okay, so what's nice is you can solve this thing 2 ways. So if I want to solve it in terms of speed, I get this very nice equation. And then if you, instead of using speed, if you use flow rate, again, I'm going to spare you the algebra. We've had enough algebra for one day. But if you put the flow rate in, which incorporates A and volume, and you solve this, you end up getting the following. You get this creature. Which must be put in this box. So again, these are just algebraic arguments. They're not terribly difficult. If you want to suffer through them, by all means do it. And this flow rate equation, which has a name, it's like Puswayle's. I don't know how to pronounce it. I should Google it and learn. Puswayli or Puzelli law or equation. It's very, very, well, I mean, I'm asking you to describe these things on the homework, but it's very nice in that, you know, if you've, the great example for this thing is thinking about, you know, you're administering, you know, medicine through an IV. You know, you have the saltwater bag, as I like to call it. And what changes and how do you change flow rate and pressure? Do you use a longer tube? Do you use a shorter tube? Do you change the diameter or the radius? All that stuff. And so this equation, again, it's not, this is an ideal situations. But you should go through drawing a picture of this and labeling what does P1 represent, P2, and all that. Now the book goes through all this, but again, I think it's useful for you to do it on your own, and then see sort of what the book or what the internet says. That's just my opinion on learning. Does anybody have any questions about this? Comments? I don't know why I ask. You guys never do. You just say no. And then once in a while, someone will chime in and say, no, we're good. Like the official spokesperson. All right. If you guys don't have questions, I say we call it a day. And then if you do have any homework, lingering questions, email me or ask on Wednesday. And then we'll pick up then. Any questions? Going once?
No, we're good.
I knew it, Ryan. There we go. All right, guys. Take care. Have a good 46 hours or whatever it is, 45 hours until we meet again, 45 and a half. Be safe. Take care.